Welcome to your section 8.3 notes. Today we're going to get into more simplifying with radical expressions. So we have different rules that we can use for radicals. Our first rule that we had is what we call the power rule. And what the power rule says is if you have two radicals that have the same index, so in this case our index is n and n. So as long as your indexes are the same, you can take your radicands, which in this case are a and b, and you can multiply them together and put them underneath one giant radicand of the same index, or one giant radical with the same index. So here we have the square root of 5 times the square root of 7. So since they're both square roots, we can make this the square root of 5 times 7, which would be the square root of 35. For part B, we have the square root of 7 times the square root of 11, so that would be 7 times 11. And then we have x, y, z, and we can just leave that as is. Now notice in the directions it does say the words, assume that all variables represent positive real numbers. So because we have that, now that eliminates the need for having to put absolute value signs around our radicals when we go to simplify. Here we have a cube root of 3 times the cube root of 12. So that would become the cube root of 3 times 12, which is the cube root of 36. For D, we have the 6th root of 10 m to the 4th times the 6th root of 5 m. So when I multiply all those together, I get a 6th root of 50. Now remember, m to the 4th times m, we add our exponents, so that's going to be m to the 5th. All right, don't make it any more complicated than that for now. We'll get a little bit more challenging as we go on. This is almost all. Okay, here we go. Next one. Here we have a 4th root of 2 times a 5th root of 2. Now, because my radicands or my indexes are not the same, I just can't multiply straight through. But what we can do is some easy manipulation. So using what we learned back in section 8.2, I can turn this into 2 to the 1/4 power times, and I can turn that into 2 to the 1/5 power. Now we have like bases. So what do we do with our exponents when we have like bases? We add them together. So now I have to figure out what 1/4 plus 1/5 is, making a common denominator of 20. Makes that 5 over 20 and 4 over 20, so that goes to 9/20. So that's 2 to the 9/20. And because I started as radicals, I should finish as radicals. So remember, your index is in the denominator, so that's going to be a 20th root of 2 to the 9th. And we can just leave it like that. Quotient rule for radicals. So the same thing applies. If you have an nth root of a fraction of a divided by b, we can separate it and do the nth root of a over the nth root of b. So for a, we have the square root of 16 over 25. So I can turn that into the square root of 16 over the square root of 25, which the square root of 16 is 4. The square root of 25 is 5. For part B, I have a square root of 7 over 36. So separating that gets me the square root of 7 over the square root of 36. The square root of 7 does not simplify, so we're just going to leave it. And then the square root of 36 is 6. Cube roots. Let's see if we remember our cube roots. Now remember, we can have a cube root with a radicand of negative. So I'm going to make it at the cube root of negative 8 over the cube root of 125. Well, the cube root of negative 8 is negative 2. The cube root of 125 is 5. If you did not know that, you could use your calculator and type in the cube root of 125. For D, I'm going to separate this to the cube root of 7 over the cube root of 216. Cube root of 7 is not anything in particular, so we're just going to leave it as is. The cube root of 216, when I use my calculator, tells me it is 6. All right, now we've got some variables in play. The fifth root of x over 32, so that becomes the fifth root of x over the fifth root of 32. Using my calculator to come up with the fifth root of 32, I'm assuming that's going to be 2. It is 2. The fifth root of x does not simplify, so we get the fifth root of x all over 2. All right, so now those were quite easy because there wasn't too much simplifying that was necessary to do. So now what's going to happen is we're going to end up with radicals where we need to simplify it further. So conditions for a simplified radical. Number 1, the radicand has no factor raised to a power greater than or equal to the index. Number 2, the radicand has no fractions. Number 3, the denominator contains no denominator contains a radical. So we cannot leave radicals in the denominator. And number 4, exponents in the radicand and the index of the radical have no common factor except 1. Okay, so the radicand has no factor raised to a power greater than or equal to the index. It's probably the easiest one to notice. Can't have fractions as a radicand. We can't have radicals in the denominator, and our exponents in the radicand and the index of the radical have no common factor except 1. All right, so simplifying the square root of 24. So again, when we were talking about this earlier, I'm going to try to find out of my perfect squares. So my perfect squares are 4, 9, 16, 25, 36, 49, so forth. I'm going to try to find my largest perfect square that divides into 24. Well, that would be 4. 4 times 6 is 24. So the square root of 4 times the square root of 6 is the same as the square root of 24. The square root of 4 goes to a 2, and the square root of 6 doesn't simplify any further, so it would be 2 root 6. If I do 108, my largest perfect square, well, 108 divided by 9 is 12, but that's making me feel like I can go a little bit higher than that. 108 divided by 16 is 6.75, so that's not it. 108 divided by 36, there it is. So 108 divided by 36 is 3. So 36 is the perfect square I want. So 108 is the same as 36 times 3. Oops, put your square roots above them. The square root of 36 is 6, and you're left with a square root of 3. So 6 square roots of 3. If you would have went with the 9 and 12, that would have been fine. It would not have been simplified all the way, because you can simplify the square root of 12 further with 4 and 3. And 4 is 2. So then you would take your 2 and your 3 and multiply them together to get the 6, and then you are left with the square root of 3. Fourth roots. So let's think about our perfect fourths. 2 to the fourth is 16. 3 to the fourth is 81. 5 to the fourth, oops, I skipped 4, is 625. 4 to the fourth is 256. Okay, so out of those perfect fours, which one divides into 162? Well, 162 divided by 16. So 162 divided by 16 is 10.125, so it's not that one. 162 divided by 81, there it is, divided by 81 is 2. So my two branches are going to be 81 and 2. Now I'm going to take the fourth root of both those numbers. Well, the fourth root of 81 is 3, all right, because this was 2 to the fourth, 3 to the fourth. So that goes to a 3, and I'm left with a fourth root of 2, and then we just have to bring down this negative in front. So that simplifies to -3, fourth root of 2. Cube roots. I'm going to make a list of cube roots. So 2 to the third is 8. Oops, I probably don't even need to go further. 3 to the third is 27. I've now exceeded my number, so it's got to be 8. So 8 times 2 is 16. Now I'm going to do a cube root of both of those, because the cube root of 8 times the cube root of 2 is the same as the cube root of 16. Cube root of 8 is 2, and you're left with a cube root of 2. All right, so now let's throw some variables into the mix. Now we're back to square roots. So we know our perfect squares, right? So 4, 9, 16, 25, 36, 49. What is the next one? 64, 81, and so forth. Okay, so we got 16. Well, 16 is a perfect square, right? So what I'm gonna do is I'm gonna separate these individually and then combine them together. So maybe that'll be less confusing. So the square root of 16 we know is 4. So that one is done. Now, m to the third. So again, remember my index is 2. So isn't this the same as m to the 3/2, right? So how many times does 2 go into 3/2? Well, it goes in once. So isn't that the same as m to the 1 times m to the 1/2? Isn't 1 plus 1/2 3.5? Yes, it is. So what we can do is, this is the way I think about it. How many times does 2 go into 3? It goes in once. So that means I can take out 1m. And I'm going to be left with 1m underneath. Or maybe even this is better. Maybe I should do this. M to the third is the same as m squared times m. So when I take the square roots of those, the square root of m squared, how many times does 2 go into 2? Once. And I'm left with a square root of m. So this is outside of a radicand. This is outside of a radicand. So I'm going to put those together as 4m. And we're left with a square root of m. Okay, so let's just quickly kind of go through that. So if I had m, the square root of m would just be the square root of m. The square root of m squared would be m, right? Because 2 goes into 2 once. The square root of m to the third is 1m square root m. The square root of m to the fourth, well, how many times does 2 go into 4, would be 2. The square root of m to the fifth, well, how many times does 2 go into 5? Twice, with 1 left over. You kind of see the pattern? The square root of m to the sixth, how many times does 2 go into 6? 3 times. The square root of m to the seventh, well, how many times does 2 go into 7? 3 times, with 1 left over. So notice how all the odds just are left with the square root of m. It's kind of your thought process that you should be doing. Okay, so let's go over to B. I'm going to do my 200. Let's start there. Which perfect square goes into 200? I don't have it listed, but hopefully you notice that's 100. Square root of 100 is 10, and you're left with a square root of 2. So I'm just going to box this so I remember that stays on the outside. Now let's do the square root of k to the 7th. How many times does 2, my index, go into 7? It goes in 3 with 1 left over. So I'm going to put this in a box because that's going to go outside. Now we have the square root of q to the 8th. Well, how many times does 2 go into 8? 4. I'm going to put that in a box because that's no longer underneath the radical. So all the stuff that's in a box, I'm going to put outside. So 10, k to the third, q to the fourth. And then everything left underneath a radical, so 2 and a k, is going to go underneath one big radical. And that would be my simplified form. So all my exponents, 1 and 1, are smaller than my index of 2. So I know it's simplified. 2 doesn't have any other factors besides itself and 1, so we know that's simplified. And we're done. All right, so let's go to cube roots. So my cube roots, remember, 2 to the third is 8, 3 to the third is 27. I don't think I have to go any higher right now. So I'm going to separate this. The cube root of negative 8 is negative 2. No radicals left. The cube root of x to the fourth. How many times does 3 go into 4? 1, with how many left over? 1. So that's going to simplify to x cube root x. Now make sure you guys remember to keep your indexes in there. Now we're going to do a cube root of y to the fifth. How many times does 3 go into 5? Well, once, but this time we have 2 left over. So I'm going to put an exponent of 2. So this goes on the outside, this goes on the outside. So let's put those together. So negative 2x cube root of what's underneath, x and a y squared. Okay, now let's go to our perfect fourths. My first perfect fourth, 2 to the 4th is 16. I don't think I need to go any higher than that because that's where we're going to be. So the negative 4th root of 32. So that's going to be 16 times 2. The 4th root of 16 is 2. And then we're left with a 4th root of 2. And now I have to do a 4th root of y to the 9th. Well, how many times does 4 go into 9? Well, 4 goes into 9 twice, so that's going to be a y squared on the outside. Well, if 4 times 2 is 8, and I need to get to 9, I'm going to have 1 left over underneath. So put the boxes together. So 2y squared, 4th root, 2y. Don't forget to include the correct index. Oh, I forgot my negative. Bring that down. Now, because this says assume that all variables are positive real numbers, I don't have to worry about putting absolute value signs around anything. Though I technically wouldn't need to put an absolute value sign around this because squaring a y would make it positive no matter what, right? And I don't have to worry about absolute value signs with the 3 because that's an odd index. Okay, next one we have the 9th root of 5 to the 6. Well, the 9th root of 5 to the 6, let's think about this. That's the same as 5 to the 6 over 9. Well, that 6 over 9 reduces to 2/3. So I can just rewrite this as the 3rd root, remember your denominator is your index, of 5 squared. So I can simplify it that way. For B, again, we can think about how many times does 4 go into 2. Well, it doesn't, so I can turn this into a fraction. So p to the 2 over 4 is the same as p to the 1 over 2, which is the same as the square root of p. Remember, your index is in the denominator. Okay, and here I think is our last one. So here we have a square root of 7 times a cube root of 2. My indexes are not the same. My radicands are not the same, and my indexes are not the same. So what can we do? Well, let's convert them into fractional exponents. So the square root of 7 is the same as 7 to the 1/2. The cube root of 2 is the same as 2 to the 1/3. I don't have like bases, so I can't just add like we did in that one that was previous, where we had 2 and 2. So what we can do is try to get the same denominators, because if they both have the same denominators, then they would have the same index. So what would be a common denominator between 2 and 3? Well, 6. So we multiply that by 3 and 3, and then we have 6 and 2. And then what do we can then convert that, sorry, my phone off, to the 6th root of 7 to the 3rd times the 6th root of 2 squared. And then combine those together. We're going to do the 6th root of 7 to the 3rd times 2 squared. So I'm going to get my calculator out to do that. 7 to the 3rd times 7 to the 3rd times 2 squared is the 6th root of 1,372. Okay, so if you don't have like indexes, you don't have like radicands, then create rational exponents, create common denominators, and then take it back to being a radical. Okay, that concludes your notes.